Welcome to the lecture series of Antenna and Wave Propagation. I am Mareddy Anusha, Assistant Professor in the Department of Electronics and Communication Engineering, B.V. Raju Institute of Technology, Narsapur. In this video, I am going to give concepts about the antenna parameters. In continuation with the earlier lecture, in antenna and wave propagation course, we are going to discuss about some more antenna parameters. Those are nothing but effective area and effective height or effective length. So in this one, the effective, what is the effective meaning? So how effectively the antenna is going to be operated as a transmitter or receiver. So in generally the purpose of the antenna is we are going to use the antenna as a either transmitting or receiving EM waves. So or EM energy. So how much of the effectiveness we are going to be calculated from that antenna. In that one, to represent that effectiveness, the major two parameters it was contributed toward to the antenna is effective height as well as effective area. So the first parameter is effective area. So the effective area can be called as capture area or effective antenna area. So the effective area, it will defines so how much of the antenna extract the EM energy from the traveling waves. So from the concept of that one, so the effective area, so it can be defined as it is the ratio of how much of the power received of that antenna to the pointing vector. So let us say to get the expression for the effective area, let us consider receiving antenna. Let us consider antenna will be a receiving antenna. In generally, we are defining that it may be defined as the ratio of the power received at the antenna load terminal. So that means to derive the expression for the effective area, the notation for the effective area is nothing but AE, effective area or capture area. So to define that, I am going to consider the receiving antenna. So from this one, the ratio of power received at the load terminals of that antenna. So that means I am going to consider here one receiving antenna. So here this receiving antenna must be terminated with the load impedance. So that at the terminals of the receiving antenna, I am going to be terminated this with the load impedance. So that the power received at the antenna load terminals. This is the parameter. So to the pointing vector. So that is nothing but a P. So then we'll write expression for the effective area. AE is equal to, so it is W by P, where W is nothing but the parameter, the notation, it represents the power received of that antenna to the pointing vector. In generally, the units for the power is watt, and for the pointing vector is it is watt for meter square, and then the units for the effective area is meter square. Now, so from this one, to get the expression for AE, now we are going to get the expression for W. So that is nothing but the power receiving of the at the terminals of the receiving antenna. Now in generally, we'll write the expression for the receiving power. So W is equal to, this will write in generally it is equal to I square RMS into RL. This is the generalized expression for the power. The same concept I am going to apply it for the antenna also. So that is nothing but W is equal to I square R. So I'll write it as I square RMS is equal to RL. Why? Because here we are going to terminate the receiving antenna with the load impedance. So that I am going to consider it as a RL. Now from this one, so here to get the expression for I, now to get the expression for I. So what is our concept here? The antenna which can extract EM waves from the traveling antenna. So here what is my assumption? Here I am going to replace this receiving antenna in the field of plain polarized traveling waves. So for that one, what happens? This antenna which can extract the EM waves from the traveling waves. So that will replace, to get the expression for IRMS, will replace this antenna with the equivalent circuit. Then for that one, here I am going to consider the Thevenin's equivalent circuit. So here the Thevenin's equivalent circuit for this system is, so already we have the load impedance. Here we have already the load impedance. So here in place of antenna, so this I am going to represent this with the antenna source as well as antenna impedance. Now this is the equivalent circuit for this receiving antenna with the terminated load. Now, so from this one, we are going to calculate the expression for the I. In generally, I can be written as V by R in general expression. But here V is nothing but, so this V is nothing but is the induced voltage at the load terminals, and this RL, here we should write RL is nothing but the total equivalent resistance of this what we can say equivalent circuit. Now we'll write it as a IRMS. So I square RMS is equal to the Thevenin's voltage V by equivalent resistance R. So it will be written as V by, this R is nothing but what the equivalent impedance. So this will be written as ZL plus ZA. Why? Because this is having, it represents the receiving antenna and it is terminated with the load impedance. By combiningly, the total impedance will be the ZL plus ZA, and the V is nothing but the Thevenin's voltage. Now we'll write it as a V by ZL plus ZA, where ZL is nothing but the load impedance and ZA is nothing but the antenna impedance. Now we can write the expression ZA is equal to, if it is the complex antenna system, so ZA can be written as RL plus ZXA. Similarly, if we consider for the load also, so if it is also the complex system, so we can write this expression as V by, so V by RL plus ZXL plus RA plus ZXA. Now I'll write it as a, I'll take mod of this I. Then this, the mod of I is equal to, it will be written as, so V by mod V, so it is written as a mod V divided by root of RL plus RA whole square plus XA plus XA whole square. So this is nothing but IRMS. But we need expression for what? AE. So it is equal to W by P. This is the expression where the W is equal to, what we'll write? So it has a I square RMS into RL. Okay. Then from this one we are going to calculate the expression for I square. So for that one, here I am going to write it as a I square RMS is equal to, what I can write it as a V square by RL plus RA whole square plus XA plus XL whole square. So this is what I. Then we are going to write the expression for W. This is nothing but what? I square RMS into RL. So we'll write it as a V square RL by RL plus RA whole square plus XA plus XL whole square. Now, so we are going to calculate the effective area. Now I am going to calculate the expression for effective area. Then AE is equal to, it will be, so the receiving power to the pointing vector. Now I will write the expression for V square RL divided by RL plus RA whole square plus XA plus XL whole square into, here we have the pointing vector P. So this is the expression for effective area. So this is the, what we can say, that this is the finalized expression for effective area or capture area or antenna area. So it is what AE. This also can be written as it is in some of the textbooks or some of the notations. It can be written as A also. So then, so for example, let us say this is my effective area. For example, from this one, so I want to calculate the maximum effective area. So at that time, what is the condition? So to calculate the maximum effective area, that I'll write it as a AE max. That means in the entire effective area, I am going to extract the maximum effective area. So to calculate that one, we have one condition. Here what we can say, that whatever the receiving antenna, it will be extract the energy from the traveling waves. It could be delivers towards to the load terminal. So the when the maximum energy can be delivered to the load. So at that time the conditions are what? XL is equal to XA. This is the one of the condition. And in generally RA is equal to, we'll write it as a RR plus RL, where RR is nothing but it represents the radiation resistance and RL it represents the loss resistance. Let us assume that the loss is very less, so that we can write if RL is equal to 0. Now replace this in the expression, so we can write RA is equal to RR. The same I am going to substitute in this previous expression. So that is nothing but AE. So that is nothing but AE is equal to, here I am going to replace this with this expression. So what I am going to write it as a, so to calculate the maximum effective area, AE max is equal to, this we can write it as a V square RL divided by, so what I am going to write, V square RL divided by, in place of what, RA, this is nothing but what, in place of RA I am going to write it as a RR. So RL plus RR whole square, where it is XL plus XA is equal to minus XL. So it will be, the term will be the 0, right, into P. So this will be written as into P. Now here again what happened, the radiation resistance, here the load resistance, what happened, here we can say that here the entire energy it will be delivers from what we can say from antenna to the load. So that what I can write here, this RL is nothing but RA, so that this RL is nothing but, so I can write RL is equal to RR also. So you can replace with the any one of the parameter. So in the numerator I have RL term, so in the denominator also I am going to replace RR with the RL. So RL plus RL whole square into P. Now we will write it as a V square RL by, so this what we can write, So it is a 2RL square. It is 4R square L into P. So here in the numerator, denominator terms are there. So AE max is equal to, we'll write it as a V square by 4RL into P. So this is the expression for the effective area. Then the final expression, the maximum effective area, so is equal to, it is V square by 4RL into P. So this is the way to calculate the effective area of the any antenna. In generalized expression is, if you consider the radiation resistance, losses and the antenna resistance also, then the expression will be V square by RL plus RA whole square, and this is the expression what we have. So this is the expression. We consider all the parameters to calculate the effective area. Or else we want to find out the maximum effective area. So that means when it will be, when the maximum power will be transferred from antenna to the load, then the conditions are, so when XL is equal to minus XA and RA is equal to the radiation resistance or the load resistance. So at that time only we can transfer the maximum power from antenna to the load terminal. So then the final expression for the effective area is AE max is equal to V square by 4RL into P. So this is the way. So if you know the Thevenin's voltage or the induced voltage at the open terminals, and we know the load resistance, then easily we can calculate the maximum effective area of the antenna. So this is the way to calculate the parameter of the any antenna, whether it could be a transmitter or receiver. So here I have taken example as a receiving antenna. Now along with this effective antenna aperture, so we have some more area parameters related to the antenna. So those are nothing but, one is a scattering area or scattering aperture. Earlier we were calculate the effective area. Along with that, so in the by the calculation of the effective area, we have so many parameters like radiation resistance, loss resistance, these all will be there. So these each individual contributes to calculate the aperture of that particular antenna. Let us say along with the effective area, we have some more parameters. So those are nothing but scattering aperture and one more is loss aperture. So here how can we define the scattering aperture, and the notation is, however earlier we were defined with the effective area, and the one more is scattering aperture. So here scattering aperture, so the scattering aperture, then the notation here I have considered it as a AS. So here this scattering aperture is nothing but, so this scattering aperture, it corresponding to the what we can say losses in the radiation resistance. In the expression we have RL is equal to, RL say that it RA is equal to, we'll write it as a RL plus RR. So here this RR represent the radiation resistance, L represent the loss resistance. So in this one, this RR, this radiation resistance corresponds to the scattering aperture. Now as well as same here, this loss parameter, it represents the loss aperture. It corresponds to the loss aperture. So we can write the scattering aperture AS is equal to the same expression what we have written earlier. So but there we have written as a I square RMS RL by P. But for this one, here we are going to write it in terms of radiation resistance. In the same way, for loss aperture also same thing, I square RMS. So it represents this parameter represent the loss resistance. So that by that we can write it as a V square RL by RL plus RA whole square plus XL plus XA whole square. Here this RL represent the loss resistance. This one represent the load resistance. That difference should be there. Okay, then by combiningly all these apertures, we call it as a collecting aperture. So that is nothing but collecting aperture. So here the collecting aperture is the sum of all the antenna apertures. All the antenna apertures means the first one what we were calculated nothing but effective aperture, the second one is scattering aperture, and the third one is loss aperture. By combiningly, we will calculate the collecting aperture. Now, so from this one, so now from this all the effective areas, we are going to calculate the efficiency. That means the ratio of scattering aperture to the effective aperture, it can be called as scattering ratio. And the notation in generally we are taking it as a beta. So we can define that scattering ratio beta is the ratio of scattering aperture to the effective aperture. Always the most what the typical values, the best case for this scattering ratio, these values are beta lies between 0 to infinity. So it could be any value in between 0 to infinity. This is about the effective area. So from this effective area, we are going to calculate the aperture efficiency also by considering all these scattering as well as what we can say effective area and what the physical area of any antenna. We are going to calculate the aperture efficiency. So in generally the way how we are going to calculate the efficiency, so in generally it is the ratio of the how much we got in the output to the input. The same way, so here the effective efficiency, aperture efficiency, it will be defined as is the ratio of the effective area, how much of the EM waves extracted from the antenna to the physical aperture, where AP is nothing but the physical area of that antenna. A effect, so RAE, it is nothing but the effective area. So the ratio of AE to the AP is called as aperture efficiency. So this is the way how we are going to calculate the aperture parameter of any antenna. This is all about the effective area or aperture of the antenna. Now, so the next parameter what we are going to calculate is effective length, and the notation for this one, and the notation for this effective length is LE, or it can be called as effective height also. It can be called as effective height also. So it will be taken as HE. Right. The same again here also, how in earlier it represents the effective aperture or area of that antenna. Here also the effective height, it represents the effectiveness of the antenna, how much effectively the antenna can be used as a receiving antenna or a transmitting antenna. It represents effectiveness of the antenna. So in generally we can define it is the ratio of, so the effective height or effective length, it will be the ratio of what we can write earlier. We have written it as the effective area will be the ratio of W by P, but it will be written as V by E. So that means it is the ratio of V is nothing but induced voltage, where E represent, it will be the induced voltage at the open terminals to the electric field strength. To the electric field strength. Now I can define that the effective length is the ratio of induced voltage to the electric field strength. So in generally in this one, this V, it associates with the effective area. So V, the induced voltage V, it associate, already we derived expression for AE. So to get V, so we can calculate, we can take V from effective area. Now I can write to calculate V. So I'll consider the expression of AE. So what we have written expression for AE? AE is equal to what we have written here, V square RL divided by, so we have written here V square RL divided by RL plus RA whole square plus XL plus XA whole square into P. Now, so into P. Now, what here I am going to write, so I need V here. So from this one, how I am going to write the expression for V. So this one we can write V square RL is equal to AE into P of RL plus RA whole square plus XL plus XA whole square. Okay, now here I have considered only V square into RL. Now here I am going to write the expression for V. So V is equal to what I can write it as a AE into P divided by RL into RL plus RA whole square plus XL plus XA whole square. Here we have the square term, so we'll write it at the square root. Okay, so this is the expression for V. But here P is equal to what we can write here, these pointing vectors, since this pointing vector P is equal to, we'll write it as a E square by Z. Now I'll replace V with V is equal to what I'll replace? V is equal to AE into, so in place of P I am going to replace this pointing vector with the electric field strength or electric field intensity. So this will be written as AE into E square by Z into RL. What I can write it as a RL plus RA whole square plus XL plus XA whole square. So this is under root. So this is the expression what we got expression for V. Now but I need the expression for V by E. Now let us take it as a E will be the outside of this one. Then here again also, however we were calculate the maximum effective area. So here also I am going to consider the maximum condition when the maximum power will be transferred from antenna to the load. Here also I will consider, let us say here also, here this one also I am going to calculate this one. Let us consider it will be the, here I will write, let us say if it is for receiving antenna, if the receiving antenna, if it will be the receiving antenna. Now, so if it is a receiving antenna case, what we have, V is equal to, so here I have taken out E as outside, then I will write it as a V by E. So we are going to calculate the expression for what, LE is equal to, so I have extracted V from the out of the root. So what the remaining parameters we have, V is equal to root of AE by Z into RL. So we'll write it as AE by root AE by Z into RL. So here we have the expressions. What we have, RL plus RA plus XL plus XA. Here for this one the maximum power will be transferred when XL is equal to XA, when XL is equal to minus XA. So that means this value will be the 0. This value will be the 0. Here the condition is what, RA will be equal to RR. I can replace this with the either RR or RL. So that here RL is there in denominator, I will write it as in terms of RL itself only. So here what I can write, so RA is equal to Here I am writing it as a RA is equal to RL. Now it is 2RL square. So here what I can write, into 2RL square. So it will be written as V by E is equal to, so this is what AE into, this is what we can say, 4RL square divided by 2RL under root. So this one cancel. So I can write it as what, root 2AE into RL under root. So this is what LE is equal. So I can replace this with the RR also. Now here what we have, so divided by RL. So here this one is 2 RL square. This is 4 RL square. Okay. Then, so this is the expression what we have. Actually this one is RL. So if I was taken it as a RL is equal to the radiation resistance of antenna. So I can written it as a LE is equal to root of 2AE into RR. This is the expression what we have for effective length, as well as it was for effective height of the receiving antenna. Now the next parameter, for example, let us say earlier I have calculated for the what effective height of that receiving antenna. Let us consider it as a transmitting antenna. So if it is a transmitting antenna, then if it is a transmitting antenna, now, so for this one, how the way we are going to calculate the effective length. So here the effective length is the length of an equivalent linear antenna. Why? Because here I was considered as a transmitting antenna. To represent that one, here I have taken the example as a dipole. For this dipole, the actual length of the dipole will be L I am taking. So from the entire L, the actual height, here the effective length will be LE. So if LE will be the effective length, now, so here what it represents, the E represent what, electric field direction. So then the current I of Z, why? Because here I was considered the propagation towards to the Z direction. So whatever the current contribution at the terminals of the antenna, that I have taken it as a I of Z. So here I of C is nothing but the current at the center point. Now, so what happens? I am replacing this with the equivalent linear antenna. So it has the same current I of C at all the points. So I of C is nothing but the current at any point. Now, along its length, then the radiates the same field intensity E as the actual antenna. Now, the way how we are going to calculate the effective length of this antenna, LE is equal to 1 by I of C integral of minus L by 2 to L by 2. Why? Because this is the length of the antenna. So if it will be the minus L by 2, if it will be the positive side plus L by 2, then I will taking the limits as minus L by 2 to L by 2 I of Z into dz. So this is the formula to calculate the effective length of the transmitting antenna. Here the parameters, the illustration for the transmitting antenna. So for this one, I of C is the current at the terminals of actual antenna. This one, I of C, and I of Z is the current at any point Z of antenna. I of Z will be the anywhere if you want to calculate the here or anywhere, this will be calculated. Why? Because here I am considering the propagation is towards to the Z direction. Now LE will be the effective length and L will be the actual length. This will be the small n and this will be the LE. Now this will be written as the effective length is equal to 1 by I of C into integral minus L by 2 to L by 2 I of Z into dz. So this is the way to calculate effective length of the transmitting antenna. Earlier case what we derived, this is to calculate effective length or effective height. This also can be called as effective height. So this will be effective length or it will be called as effective height also. This will be written as a HE. So what we can say, we can derive the, if it is a receiving antenna case, if the same case we will consider it for the transmitting antenna. Let us say it is a for transmitting antenna, how the way we are going to calculate the effective length for the transmitting antenna. For that one, I am going to consider one small illustration, that is nothing but one antenna. It is having the length L. So here L is nothing but my actual length. So this antenna is having the effective length is equal to LE. How we are going to get the expression for this LE from this illustration? So here I am going to consider what a dipole. Here I was considered as a dipole antenna. If the total length will be L, so then it will be the positive side will be the plus L by 2 minus L by 2. And again here what E is nothing but the field intensity. Here my assumption is what, here the propagation is towards to the Z direction. That is why I was taken it as a I of Z, where I is nothing but the current distribution of the antenna terminals. I of Z is nothing but the current distribution at any point. Then where I of C is nothing but the current distribution. I of C is nothing but the what, it has the same current I of C at all the points. So with respect to the center. Now the same whatever I was explained, that was defined here, where one of the parameters I of C, the second one is what, I of Z. This is a current at any point of Z of antenna, and LE will be the effective length, what we are going to write the expression, and LE the actual length of the antenna. Then hence for transmitting antenna, how we are going to write the expression? So this will be written as the effective length is equal to, so I of C into effective length is equal to integral of, that means what, integral means what it represents, it is sum of the current distribution at the each individual point. So here to represent that one, I have taken it as integral minus L by 2 L by 2 I of Z into dz. So that means what it represents. So I of Z is current distribution at any point, somewhere here or here, somewhere there. So this is sum of the all points. So that I have taken integration. Here what is my length? So it will be from minus L by 2 to plus L by 2. To represent this one, I have written this as the expression. Now, but actually we need what? This effective length. So then this LE is equal to, from this one we have written as a 1 by I of C into integral minus L by 2 to L by 2 I of Z into dz. So this is the way we are going to calculate the effective length of transmitting antenna. So these two parameters, effective area or effective length, it represent whether it could be a transmitter or receiving antenna, the way how much the effective the antenna can extract or can radiate the EM waves. So this is all about the antenna parameters. So thanks for watching the video.
Like, share and subscribe. Hit the bell icon for more updates.